You doing? Good, great, awesome. All right. So I'm JP Camara. I'm going to talk about real-time collaboration with Rails, AnyCable, and Yjs. And just to give a little bit about myself, so you'll find me most places online as JP Camara. I do a lot of blogging about Ruby and concurrency and things like that. And I'm also a principal engineer at a company called Wealthbox, which is a CRM for financial advisors. So when I say collaboration, real-time collaboration, what am I talking about? And so this is actually an example from Wealthbox, from the application I work on, where people in certain situations, did my mic just go off? Oh, okay, sorry. Basically, people can come together into a single document or a single source of information and be able to collaborate on it at the exact same time, and without any locks on the server or anything like that, and be able to see that information, that automatic immediate feedback. And so part of the reason that I'm doing this talk, the inspiration for it, and where I've gotten a lot of the knowledge about it, so we released an AI note taker. We use a lot of real time with that. We use AnyCable for it, and we also do some real-time collaboration in there. So the tech stack we're going to talk about, it's going to include Ruby on Rails, unsurprisingly. We're going to use Yjs, which is a tool for something called CRDT, and I'll explain what that means and how that works later on. And then the glue that's going to bring it together in this case is going to be AnyCable, which is an ActionCable compatible WebSocket server. And so I'm going to break down the talk into what I call collaboration, the hard parts. You know, they're not impossible. They're things you can overcome, but I think they're the things that you have to kind of think about when you're creating a real-time collaborative experience. That includes managing connections, so those WebSocket connections that you're going to be working with. Trying to keep your latency as low as possible. Being able to replay history. It's really important that if you disconnect and reconnect, you don't lose things as you're going through. Concurrent edits and out-of-order delivery, and making sure those converge into a consistent state. Cursor and typing awareness, so you feel like you're in a document together and you see what other people are doing. And then scaling persistence, being able to store the information about those operations that you're performing and not have a million things in the database that you need to send people all the time. So we'll start with managing connections. So generally in real-time collaboration, every user has their own WebSocket connection. You know, we'll start by talking about ActionCable a little bit, since that's what AnyCable is compatible with. So it's WebSockets on Rails. In Rails, it uses asynchronous I/O and threads to get that to get the WebSockets working, and that gives you that persistent bidirectional connection. So the typical, out-of-the-box development setup anyway, is your Rails server does both serving up your web application and also the WebSockets that connect to it. Everything is just going through that single Rails server. To be able to publish to different people, you store things in the database and distribute those out as broadcasts. And then when you get into more of a production setting, you probably will have your regular Rails application serving up the web, and then you have a separate application that's still just the Rails code base, and that's the way you scale it up is just by essentially deploying more instances of your server. And so if we're going to do a code example, what you do with ActionCable is you break it down into channels. When you start a channel, you create a consumer, you're consuming that WebSocket. And so here we create a consumer, and then we want to subscribe to a particular channel. So in this case, we're subscribing to the chat channel. On the Ruby side, it being Rails and Ruby, it's a pretty intuitive interface. You just create this chat channel class. When a subscription comes through, you can usually do some auth logic and different things here, but in this example, I'm just automatically saying, like, you tried to subscribe, I'm going to stream information about this chat room to you. On the front end, you can say, I'm going to send information to the server. The server receives it. In my case here, I'm just broadcasting that back out to everybody. Once you get that broadcast, you receive that data on the front end and you can act on it in some way. So it's a pretty intuitive interface. Many of you have probably already seen it. So it seems fine, and it works in standard Ruby, and that's great. So why would you bother with AnyCable, and why do I use it and think it's a valuable thing for real time? AnyCable, so like I mentioned, is an ActionCable compatible WebSocket server. What I didn't mention is it's written in Go, so that comes with a lot of performance benefits to it. If I kind of lay out the things that are beneficial or I think are beneficial for real-time Both of them manage connections. That's kind of the table stakes. You get that out of Rails, no problem. You can have low latency with Rails, but it's really simplistic to do and achieve with AnyCable, and I'll get into some statistics about benchmarks there. Replaying history is something that comes out of the box with AnyCable, whereas with ActionCable, it's not something you kind of have to implement something on your own. And then cursor and typing awareness, it's not something that AnyCable gives you for free, but there's some beneficial parts of its architecture that really help with that a lot. So low latency. Real-time needs low latency. You really can't throttle collaboration. You want things to come through effectively feeling like the moment that you act on them. So if we look at benchmarking that's done between AnyCable and ActionCable, one of the things that you'll notice pretty quickly and that I've had experience with is that as you get more connections with ActionCable, unless you start scaling your servers up really aggressively, the time to broadcast can be really slow. And so the more connections you start connecting to ActionCable, you can see here that basically what that broadcast RTT is showing you is like, I send something to the server and it can start taking, you get to 10,000 connections, it can take like 5 seconds for that to get out to people. Obviously a no-go when it comes to real-time collaboration. It's okay if you're sending an update to somebody asynchronously and they're not realizing that they're collaborating with you. Whereas with AnyCable, you get a pretty steady state in terms of how those broadcasts work. Basically, I don't think it goes above a second once you get to 10,000 people, and that's on a single node. In addition, Rails is awesome, but it's pretty heavyweight. As you're going to scale this up, it is definitely going to take up a lot more memory. AnyCable, again, with a single node, can keep the memory extremely low as it's operating. And then CPU usage. So as you get to that 10,000 connections, you're just starting to max out what ActionCable is capable of. AnyCable just kind of takes it with no sweat. So ActionCable works, but AnyCable scales pretty effortlessly. And in particular, when we were implementing some of our real-time features, we hadn't had them before, and we already had a very large user base, and we wanted to know, like, we can put this thing in, and we're not going to have to figure out how to scale a brand new type of infrastructure in our app. It's lightweight and tailor-made for WebSockets. And it decouples your WebSockets from scaling your Rails server. So you get to continue tuning your application for web requests, which is kind of what you're probably already very good at, and you let AnyCable take care of that WebSocket connection for you. And most importantly, and what we all want to see here, is that your business logic stays in Ruby. You don't have to start writing Go to be able to use AnyCable. AnyCable handles it in Go, but you get to write Ruby logic as if you were still using your regular ActionCable code. So this is going back to our example from before, where this is what it looks like to do an ActionCable. And so what would this look like if we wanted to move this to AnyCable? And because of the compatibility layers that have been put into AnyCable, this is actually pretty much the only change. You change the import to use AnyCable Web. Everything else you're used to is pretty much there, and the compatibility is really, really good. There's certain niche features that don't work as well, but I've never encountered them. How do I deploy AnyCable? AnyCable has its own binary, starts up its own server. It looks pretty similar to the previous slides. Rails will serve up your application, your WebSockets start to connect, but instead of hitting Rails, they now connect to AnyCable Go. So that's your dedicated WebSocket server. The way that AnyCable Go communicates with Rails, it has a ton of options actually, but one of the simplest ones to set up is you can say, oh, I want to just make literal HTTP requests. And so once again, you're kind of managing the type of Rails application and infrastructure that you're used to, scaling web requests. AnyCable is taking care of your WebSocket connections for you, and when you subscribe, it would send an HTTP request to Rails, and whenever Rails says, I want to broadcast to people, it sends a broadcast request to AnyCable itself. Now, it can actually get significantly more robust than that, and it's kind of amazing the different options that it has. You can obviously have multiple nodes. You saw that like having 10,000 clients, you could pretty much run pretty successfully on a single node, but you can increase that. You can also run your Rails application as a gRPC server, which just has an even lower latency in comparison to your regular web application, and it communicates with it using RPC. So one last piece on AnyCable before we start moving into some of the actual collaborative convergence stuff. History replay. So one other feature that's really beneficial here is that AnyCable comes with something called reliable streams. Basically, you can see that I'm going offline here. The other person continues to write and is still online. I'm not receiving anything. And so the moment that I go to turn my connection back on, I receive that message. With a lot of different WebSocket systems and ActionCable included, pretty much that time where you're disconnected, everything's lost. And so with AnyCable, you can specify something called a broker, and that is essentially like a cache of your messages, and you can specify how long that history is. Now here I have a history limit set to 100. You probably want it to be maybe a bit more aggressive than that with real-time collaboration because there's so many small updates, but this is a really great benefit for disconnects and reconnects as you're moving along. All right, so now we're gonna start talking about how the actual convergence, concurrent editing, conflict-free locks stuff works. So concurrent edits and out-of-order delivery. Multiple users are editing the same source. We can't guarantee when we get those updates, they can edit the same parts of the same document. So what is a CRDT? Hopefully I can say this correctly. It really rolls off the tongue. It's a conflict-free replicated data type. It's this special structure that's designed so that you can concurrently make edits, and they always eventually converge. So they always converge into your final document state as long as you have the full history. There's no locks, there's no central coordinator, you're not taking a lock in the database in the back end, you're not going back and forth between people. It's all coming together, and the system is designed to algorithmically figure out how to combine that document together. Each change is an update that can be applied in any order, eventually yielding the same state on every client. And it can work offline. So you can queue edits locally. When clients reconnect, operations can merge without conflicts. So we're going to talk about Yjs, which is probably the most popular implementation of a CRDT. It's what's called, or it's internally a linked list CRDT, where everything's represented as an item. It has various data types that work on top of it, so you can act as if you're interacting with text, act as if you're interacting with a map, or an XML element for a tree. Ultimately, it all gets mapped to the CRDT internally, but it helps you to be able to say, like, I have this particular type of structure. It helps me to represent it this way. I don't have to manage a linked list. I just say map.put. And here's a slightly simple example. You create a document. You get different data types, which actually creates them as you're getting them. And then the thing you most commonly see is when you get updates from some kind of source, you apply those updates to your document. And that comes through as a uint array. So we'll take a simple example. Text is probably the simplest thing to understand and move through in a CRDT. So I've got client A, and client A is saying, hey, let's collaborate. Inside of Yjs, what it does is creates this item that has let's collaborate inside of it. Now, the first thing that ends up happening after you write that is client B is also connected, and they receive this update. And that update gets replicated to them. And so that's where that concept of you've got a conflict-free replicated data type. Everybody who's connected to it has that same set of information being replicated to each of them. They go in and they're like, I don't just want to collaborate, I always want to collaborate. And they spelled a little incorrectly, but the CRDT allows you to insert that in there. Now that starts to not complicate, but enhance our linked list. So basically, I'm a new user. I didn't create that original content. I inject always in there. Now my linked list has this extra section to it. I'm also very excited about it, so I added an exclamation point that adds a new item into the linked list. Again, client A is still connected. They receive this always and this exclamation point from me. It replicates that data. And this is a really important part of how all of this works, is you always have to be applying all of the operations from your CRDT history. And then finally, they don't like the fact that it's misspelled. They add in the A. And you can see that it just kind of keeps growing and growing. But internally, you're just doing things like, I'm going to insert some text. We're going to show that. Actually, we'll show that in a second. But you're just doing things like, I'm going to insert some text. 1 second. And the CRDT is handling that information for you, how it stores it internally. So we're going to talk now about convergence. And so when I say convergence, I mean converging on the final state of your document, the correct state of your document. So how do you represent order between independent systems? So timestamps are unreliable. You know, some people here have a cell phone or a computer. There's servers out there. We can't say reliably that each of those timestamps is in sync all the time. They're all over the place. So we can't really rely on timestamps in a distributed system to be able to bring things together. Position is unreliable. If I go like, oh, I want to put in position 6, but you're coming in at the same time and putting text, multiple pieces of text at the beginning of the document, now my position 6 is wrong. I don't get the output that I want. And so the first part of being able to have this convergence to figure out how to coordinate these independent systems is to be able to have, it has a concept of an ID. And that ID consists of 2 parts. It's got a client ID, so that represents my interaction with a particular document, and then it's got this thing it calls a clock. And this is what's called a Lamport timestamp. It's this distributed system concept that's been around for decades. And basically, how it utilizes it to say that for a particular client, I can kind of have a guaranteed order of how I did things. I can't guarantee how other people did things, but I can say that I typed A, and then I typed L and W, and those things went in order, and I know that I can always apply those consistently. And so we can kind of see how that gets utilized here. And so I was talking about how it abstracts that linked list for you. I can just say, I have a client, I get some text, and I want to insert that text. And so it's a pretty simplistic interface. I get that item that we were looking at before. I'm client 123. I'm at clock 0, so this is basically the first thing I'm doing. And it gives me a length of 17. So I'm representing this range of potential operations that I'm doing between 0 and 17. Client B comes in, and they're very excited, and they always want to collaborate. And so they create their own item. And so now client B has 789 as their client ID. They're also starting at 0. So we have our independent sets of counters that are moving independently, but they are in order for us. But now the question is, how do we bring those into order together? So you have an order, and I have an order. How do we converge those? And so when I enter in that always, essentially I'm saying I want to insert after 6, and I want to insert before 7. And so what the CRDT does is it actually splits that item. And so it starts to create essentially a new structure. So we still have some history for each of us in terms of how our clocks move forward, but now we have to have a sense of not position, not timestamp, but relationship. And so what ends up happening is I enter in always, and what the CRDT does is it says, okay, always has a dependency on this new ID that I created. So ID 1230, it's this thing called let's. And then at the end, I have collaborate, which is dependent on always. And so we start to have this tree where there's these things called origin and right origin, where we now have both a counter that increments on each side. I have my own counter, you have your own counter, but then we have dependencies between IDs within that linked list. And that allows us to be able to say, by combining those two things together, we can actually figure out what the true order of something is supposed to be. And I'll show an example of that in a second. But so like I said, instead of positions, YJS stores the relationships to the other items. And so with that Lamport timestamp and those relationships stored together, you start to be able to have consistency. Because what I want to be able to do, in my example here, I'm applying an update. In another case, I'm shuffling the update before I apply it. I want to be able to send things in whatever order I get them. And as long as I get the full history of the CRDT, I always can say what the final state is going to be. So even though both of these come in different orders, eventually they land on let's always collaborate. And so this is a basic representation of that linked list that we had so far. We've got let's. I won't read through all of it because they're not actual full words, but essentially we're kind of showing the dependencies and the increasing clocks between our different pieces of data. And now we're going to walk through how those dependencies actually result in that state. So the first thing in my instance here I'm saying is I received an update from someone and it's just the exclamation point. So what the CRDT is going to do is it's going to say, okay, well this exclamation point, I know it's dependent on ID 1236. I don't have that yet, so I'm going to just sit on that. In addition, this is the 6th clock. So this is the 6th increment for this Lamport timestamp. I need to get everything that happened before that point. I don't have that, so I'm just going to sit on this. And so it sits and waits for the information to come in. And so my output right now is blank. The next thing that it does is I get a let's from it. Now, let's has no dependencies. It's the first counter in that Lamport timestamp, so I actually can show that information. Next, I get collaborate. Once again, collaboration is dependent on this 7893 ID. We do have 1230, but we don't have everything we need. It kind of puts it into that pending queue. And we kind of keep moving along where the CRDT itself is figuring out, do I have all the dependencies I need? If I don't, I'll wait. I'll wait until I get those dependencies. Once that gets applied, I'll use the same deterministic algorithm for sorting them, and then I'll apply that output. And then we get let's always collaborate. So even though we're out of order, we can still show this data correctly. All right, so that was most of the CRDT stuff. Now we're going to talk a little bit about cursor and typing awareness, how YJS handles that, and another area where AnyCable helps. So we need to track user presence, and we need to track editor position. So in this instance here, in that collaboration example, you may not have been thinking about it, but the cursor is constantly moving with you as you're going through that document. And in addition, things like highlighting text are being shown to other people as well. This is really important for that collaborative experience and knowing also where somebody else is in the document. What you see on the right side is that for every piece of presence and cursor information, it's just pounding, actually really pounding the server with information. There's a ton of awareness information that comes through. YJS thankfully gives you a protocol for this. It's called, it has this awareness class, and you can listen for updates on it. You hand your document into it, and you can say, hey, whenever there's an update, internally it handles like pinging the server, checking if people are still there, that sort of thing. And it says, okay, there were people added, updated, or removed, and then I have this metadata and shared information about who they were and how that information materializes. The way it stores it internally actually is also another CRDT, and so that's part of the reason that it's able to keep this cursor awareness consistently moving along. It's in a slightly different structure, but it still has a client ID and a clock, and it stores that in a map and figures out how the awareness is working. Now, this is where AnyCable comes in again, where you need data on the server for persistence. So as I'm typing in my document, let's always collaborate, that has to be stored somewhere and be able to be redistributed to other people. But you really don't need to store cursor awareness. I don't care that 15 minutes ago you were in position 5 and you highlighted a section of text. It's not meaningful to me. And so one of the benefits you get out of AnyCable is something called Whisper. So AnyCable Whisper allows you to say, you can specify that your channel is a whispering channel, I guess. And then on the front end, instead of doing send, you just say whisper to the server. And what that does is it actually completely cuts Rails out of the mix in that case. So for instance, for situations where all you care about is distributing this information out to other clients, you can do that through Whisper. It hits AnyCable and then immediately distributes it out to other people itself. And so Rails doesn't have to get involved. You take the load off of that and you get ultra low latency from it. All right, kind of the final piece of this is you may have noticed as you're going through this, everything I'm typing is getting sent to the server, and it's all being sent to the server individually as these little update packages. And so I'm typing let's collaborate, and we see that as a single item. But let's collaborate actually goes to the server like this. Like every single piece of information comes through as this binary encoded UN array. And so every piece of information is stored as an operation. It's very easy to start storing thousands of updates. They accumulate very quickly. So you really need to do something that's often referred to as compaction. So you compact history into a single update. We can take all of those updates we have, apply them to our document, and then YJS comes with something called encode state as update. You take all of those thousands of updates, you put them into one thing, and now what you can do is start serving that single update to people, and then you start getting the new updates from there. That would be kind of a pain if you had to do it on the server using Node or something. There is a package called YRB. It's a wrapper around a Rust version of YJS. You can perform certain operations on YJS docs using it. So you could say, like, I'm over my particular threshold. It has a different interface, but it's a similar concept. It's applying updates and then gives you a diff at the end. The only downside is it's not thread safe. So you have to coordinate it with a mutex, and I'm looking into whether we can fix that. So now we're going to put it all together and kind of finish this up. We're going to create our own custom YJS channel. On the front end, YJS usually talks in terms of providers. It's really just a WebSocket connection that sends your data to the server and returns it. My suggested interface here is to send your initial sync. And so I've got models for a YJS update. I've also got models for a snapshot for that compacted version. And I check, do I have a snapshot, and get me every update that's happened since that, and then combine those two together and send them to the front end. And then when you send an update from the front end, I just treat my channel as kind of a simple pass-through. In the Node ecosystem, there are more sophisticated versions of how some of their WebSocket connections work and how they encode data. In my case, I'm just passing it through. I store it. Now I know I have it, and then I just send it on to all the other clients. And then if we want to do this in an editor, a CRDT really works best with an editor that exposes a granular structured change. And so the reason I bring that up is, like, some editors work basically just off of HTML. And if you're just working with HTML strings, it can kind of work, but you really need to be able to expose the, like, XML tree effectively of that information for the CRDT to work effectively with it. And so Prosemirror, that's what TipTap uses, if you've heard of that. There's Quill, and then I'm sure a lot of people are familiar with the new Lexi editor that's being worked on at Basecamp. And I'm building a Lexi real-time version of it. It's very raw right now, but we're going to use that for this example. And so in this case, we create a Lexi editor element. For the Lexi real-time piece, because we have to hand in certain properties like a YDoc to it, I actually create the element and then I start handing those properties in. And then I will be sharing, I have a GitHub repository I'll be sharing after the conference that'll have some of the specifics of this. But we basically hand in awareness, we hand in our provider, which handles those connections to the server, and then we append that child. What I'm gonna try to do now is have people connect to this and see if the Wi-Fi and cellular networks locally can actually handle it. But basically, let's try to do some collaboration together. Let's see what happens. Oops. Oh boy, there it is. People are starting to go in. Oh boy. I will say I'm pretty sure there is some cursor awareness bugs that I have in Lexi real-time right now that you wouldn't have in other editors. I feel like I'm watching a race right now. So this is the editor portion of it. In addition, there's two other pieces that I'd like people to check out. So there's an emoji board, which allows you to just, I don't know, add in emojis and pull other people's emojis around. That one is using, the reason I created different versions of these demos is each one uses a different type of YJS structure. So the editor uses like an XML fragment. The emojis uses a YJS map to be able to throw things around. And then what I would like people to go to especially is there's a drawing page. And the drawing page, okay, looks, some people have already put stuff in there. The drawing page is a collaborative infinite canvas. It would be cool to treat it as sort of like a San Francisco RubyConf like poster board that everybody can write on. Put your name in, you can draw something on there, and that'll be stored in this infinite canvas that you can move around. One person has done something so far, and that's great. So yeah, so basically I'll be releasing the source code for this as well at the end of the conference, but I just wanted people to get a taste of some of the stuff you can kind of do. All right, I'm gonna go back to the talk. So to recap, AnyCable isn't strictly necessary, but it does help a lot with real-time collaboration. It's been very beneficial for us. Concurrent editing requires conflict-free, I meant to say convergence, I think, but I put editing there. CRDTs are the common answer, and YJS is a popular choice. And you can do real-time collaboration in your Rails app without having to reach for a node server, which was kind of a non-starter for us. But still, real-time collaboration, as you can probably kind of tell, it's kind of a lot. You can do it and successfully in Rails, but you want to make sure it's worth it. It's powerful, but save buttons are pretty nice. And so if you can kind of go with a save button, I would recommend it, but it is a pretty great option to have. And that's it. Thank you.